My name is Thomas, and in the coming 5 minutes I will present our contribution titled Online Phase Speed Estimation of Human Motion using a Moving Horizon Estimator. So the hypothesis of the work is that intuitive human-robot interactions are possible, but the robot has to be able to recognize and predict human motions. This of course needs a framework for online human motion prediction. And in previous work, we already proposed such a framework, which would take as an input an ongoing motion, which is simply a time series consisting of joint angles or Cartesian positions of a wrist, for example. And the framework would then output this green curve, which is a prediction of the currently ongoing motion. A crucial aspect in generating such a prediction was phase speed estimation, which can be interpreted as the estimation of the execution speed of the ongoing motion, because this phase speed estimation will eventually govern the temporal scaling of our predicted motion. So this is crucial, and therefore it is the subject of this contribution. So before going into detail about this phase speed variable, I first have to highlight that our framework makes use of an offline learned motion model database. So this database stores a motion model for every possible motion that we would like to recognize or predict. Now, these motion models, I won't go into detail, but these motion models often use an implicit representation of time instead of an explicit representation of time. So instead of being dependent on time t, these motion models are dependent on a phase or progress value s. This phase value is equal to 0 at the start of a motion and then progresses linearly until it's equal to 1 at the end of the motion. And the speed at which this phase value progresses is given by the phase speed variable. So this phase speed variable will then show up in our motion models, which we will then use in our framework to generate a prediction. And this set of figures then here illustrates the importance of estimating this phase speed variable as accurate as possible. If we estimate it either to be too large or too small, our prediction will not be very accurate. Only if we can estimate it quite good, then we can generate good predictions. So how do we estimate this phase speed variable? Well, first we could use an iterated extended Kalman filter, which would estimate the phase speed variable at every time instance t, and then calculate the corresponding phase value. However, a disadvantage is that the Kalman filter is only able to take into account one observation at each time instance. In contrast, a moving horizon estimation is able to take into account multiple observations at each time instance. In this case, it's able to take into account 10 observations. We compared then both of these formulations with a benchmark, and this benchmark was generated with this moving horizon estimation, but instead of using 10 observations, we would now use the full demonstration length. So this benchmark would then generate an optimal solution. Comparison then between the moving horizon estimator and the benchmark and the Kalman filter and the benchmark was done based on the estimates of the phase speed value, and we calculated then the cumulative Euclidean distance of phase speed estimates along a demonstration. So we evaluated everything on 94 squatting and 94 stooping motions, so which are real human motions, and the results can be seen in this figure on the right. So the x-axis is a time axis, and the y-axis is either the phase or the phase speed value. And these curves then represent the estimated phase speed value at every time instance of an ongoing motion. And you can clearly see here the differences between the Kalman filter, moving horizon estimator, and the benchmark values. And so what we then did was calculate the Euclidean distances between the Kalman filter curves and the benchmark curves, as well as between the moving horizon estimator curves and the benchmark curves. The results are then shown in this table. So we did this evaluation for more than 2 different formulations, but I highlight the 2 most important ones, in which you can see that the moving horizon estimator leads to a lower difference with a higher computational load. And this is then also the main conclusion, namely that the moving horizon estimator leads to a lower difference, so a higher performance, but also a higher computational load. However, we believe that both of these formulations are suitable for online use. This brings me to the end of this presentation. I would like to thank you for your attention.